Hello, everyone. Good afternoon. Welcome to today's webinar on modeling PV systems with multiple maximum power point tracking inverters. We will just go ahead and get started. Looks like we have a decent number of people on the line here. So this webinar today is the third in our 2018 series of webinars. And you can find recordings of the previous webinars on the SAM website at the link shown at the bottom of the page, sam.nrel.gov/webinars. And they're going through a lot of the new features and changes that we've been implementing for our upcoming release of SAM. And today is going to be talking about some changes we've made in order to be able to model multiple maximum power point tracking inverters in SAM, which was not previously a feature that we had available. Before I jump into the maximum power point tracking piece, just a quick overview on SAM itself for people who might not be as familiar. SAM stands for System Advisor Model, and it's a free software for modeling both the performance and the economics of renewable energy projects for a variety of different types of technologies, although today we'll be focusing on the detailed photovoltaic or PV technology. The SAM desktop version, which is what we'll be demoing today, is available for free for download at sam.nrel.gov, and the source code for the project is also available on github.com. We have versions for multiple operating systems, and we usually release 1 to 2 new versions of the desktop tool per year, accompanied by the software development kit for those programmers that are in the house here. There's also extensive support, help systems, documentations, an online support forum, and contact form for general questions for SAM. So to delve into today's topic, maximum power point tracking, I'll start with an overview of the idea of maximum power point tracking. So for some of you, it might be a little bit rudimentary, but I promise we'll get into the interesting part around bullet 4. We'll discuss what maximum power point tracking is, why you might need multiple maximum power point tracking inputs, and how that can help cut back on one type of mismatch. And then we'll jump into the live demonstration in the SAM tool itself, showing how you can model the things that we've talked about in SAM. I'll wrap up with a brief discussion on some of the current limitations of the multiple MPPT feature in SAM and things that we're hoping to improve in the future. And then I'm planning to leave plenty of time for questions at the end of the webinar today. And just a quick note about logistics. If you have a question or comment, you can feel free to type it in the questions box in the GoToWebinar interface. My colleagues who are on the line with me are going to be helping to keep an eye on the questions as they come in, and they might ask some as I go through if it's a particularly relevant question to what I'm talking about at that moment. Otherwise, we'll go through all of the questions that come in at the end, and we'll do our best to answer them. So let's get started on today's topic. So I want to go really down to the basics here and talk about what, first of all, a maximum power point is in a PV system. So when we're talking about PV modules, every module has a characteristic current voltage curve, or IV curve. There's an example shown in the upper picture on this slide here. These curves, as I said, are characteristic of the module themselves, but they also change as irradiance and temperature change that the module is experiencing. And you can imagine, as we all know, power is the multiple of current times voltage. And so if you assume that the module operates somewhere on this IV curve, each point on that curve is associated with the power. So in the lower figure, you can see the red is the IV curve, and the blue is the power that you get by multiplying the voltage and the current at that point. And as you can see from the curve, there is a distinct maximum power point, occurring usually around the knee of the IV curve. And so that is what we mean when we talk about the maximum power point of a module. So then if we move on to talk about maximum power point tracking, which is the bulk of what we're going to be discussing today. What that basically entails is that the inverter that the modules are connected to can control the voltage of the string of modules so that the panels in that string are operating at their maximum power point. The process of the inverter doing that is called maximum power point tracking. Now, I want to mention one note that's going to be important in today's webinar, which is that we are going to be ignoring module mismatch within a string. So what I mean by that is we're assuming that each panel within a string has the exact same IV curve and therefore the same maximum power point. In real life, that might not be the case due to things like uneven shading, uneven module degradation, uneven soiling. But for today, we're going to ignore that type of within string mismatch and just assume that all modules on one string are going to be operating at the same voltage for their maximum power point. So we talked about what maximum power point tracking is for an inverter controlling one string. Well, what happens if you have multiple strings? The answer is that the maximum power point tracking still works. The inverter can still operate each module at its maximum power point as long as all of the modules on all of the strings have the same IV curve. Because as we remember, the inverter is controlling the voltage that the strings are operating at. But what if the strings have different IV curves? There are a couple of different reasons that you might, in a system, have strings with different IV curves. One shown in the diagram on the upper left here is if different strings have different orientations. So that could be either a different tilt or a different azimuth. This might be more common in smaller residential rooftop systems where perhaps part of your roof is facing east and part of your roof is facing west or something like that. And the reason that that results in different IV curves is that, as you'll recall, the IV curves change under changing temperature and irradiance conditions. So if you have modules facing different directions, they're getting different amounts of irradiance, so they're operating under different IV curves, even though they might be the same module type. And that's what's shown in the bottom left picture. That is an example of an array of different IV curves at different irradiance levels for the same module and the same temperature. Another reason that strings might have different IV curves is if there are different types of modules between different strings. So one example of that could be different manufacturers of modules. Perhaps you had to retrofit your system because some panels broke, or maybe you wanted to add to the size of your system and the original panel that you had installed wasn't available anymore, so you installed a different kind. So these are just a couple of examples of situations in which different strings within the same PV system might have different IV curves. Another situation that might cause difficulty with the maximum power point tracking is what if the strings within your system have different numbers of modules in them? So here we have in the diagram one string of 6 modules and one string of 9 modules going into the same maximum power point tracking circuit. Because modules are in series within a string, the voltages are added together. So those two strings would have different voltages. But a single maximum power point tracking circuit can only operate the system at one voltage. So what happens then? Well, here's where we get into the realm of single versus multiple maximum power point tracking inverters. A single maximum power point tracking inverter would search for the voltage that provides global maximum power. And if you have some of the latter situations that we've discussed where the IV curves aren't the same for different strings, that might result in off maximum power point operation for any of the strings of modules. Now within SAM, which I'll demonstrate in a little bit, there's two different ways to model that particular piece when you have a single maximum power point tracking inverter. We have a mismatch voltage calculation that will actually replicate the behavior of the inverter itself. It will search through a range of voltages for the system and calculate what the maximum power, or what the power would be at each of those voltages, and then picks the voltage that is the system maximum to operate at. Now that feature is only available for the single diode module models, which are the most commonly used in SAM, but there are a couple that aren't single diode models. And the reason for that is that in order for us to model off maximum power point operation of a module, we need to know what the entire IV curve looks like, which is available in a single diode model, but not available in every module model. And I'll explain that a little bit more when I do the demo. The second way that we can model that in SAM is we make a simplifying assumption and we use the weighted average voltage across the entire system. One note is that this can significantly underestimate the mismatch losses due to strings operating at different IV curves when you have a highly mismatched system, and I'll demo that as well. But it is an option, A, because it takes slightly less computation time, and B, because, as I mentioned, not every module model is eligible to use the mismatch voltage calculation, which is more accurate and preferred, but if it's not available, the weighted average voltage method is an option at least. However, the other solution to having some of these situations where your strings are operating or would be best operated at different voltages, you can solve that with a multiple maximum power point tracking inverter. So multiple MPPT inverters have multiple circuits within them that can perform maximum power point tracking. So if you connect strings to different MPPT circuits, you can allow each string to operate at its individual maximum power point, perhaps resulting in greater power for the overall system. So with that brief introduction of what we're talking about from a maximum power point tracking mindset, I will go ahead and jump into a live demo in SAM. And team, feel free to interrupt if there are any questions I should tackle at this point.
Oh, you're good to go, no questions.
All right, thanks, Paul. So what I'm doing right now is starting up an instance of the System Advisor model, SAM. I'm using the open source version because this feature is still in development, and the open source version is where we do our active development. So the other caveat that I like to give whenever I demo something in the active development version is it's not totally locked down and quality tested yet. So if we encounter a bug, that's sort of par for the course when you're using things actively being developed. So I'm going to go ahead and start a new project. And I'll pick a detailed photovoltaic plant because the multiple MPPT feature is only going to be available in the detailed PV model. And I'll pick the no financial model because for now I'm going to focus on the technology model itself. Now you might notice right when you open it up, if you've used the detailed PV model before, that the solar resource page looks a little bit different. That was actually the topic of one of our previous webinars in this series. So if you're interested in learning more about that, feel free to check it out, sam.nrel.gov. You can watch the recording of that and learn more. But for now, I'm going to skip over to the changes that are relevant to the multiple maximum power point inverter case. I'm going to start with the system design page. And for those of you who are familiar with previous versions of SAM, you'll notice that there are a lot of changes on this page. I'll go through them in a little bit of detail and sort of walk you through the new operation. But the first thing I want to point out is that if you were familiar with the option for SAM to automatically size your PV system, we had to remove that option in this version of SAM. It's fundamentally at odds with the inputs that we needed to add in order to be able to model multiple MPPT inverters in a robust way. And to add on to that, as we had mentioned whenever we've done webinars on that feature in the past, the algorithm could be a little problematic. It was certainly not a perfect sizing algorithm. And it could result in it being a little bit difficult to tell what your actual system size was, especially if you were running parametrics. So in this version, we have done away with the option for SAM to size your system, and we rely on the user to size their system. But we are providing some scripts and sizing messages to help you do that in a robust way. The second thing that I want to point out that's a big change on this page is the location of modules per string and strings in parallel. In order to make the multiple MPPT inverters feature most useful, we added modules per string and strings in parallel as an option for each subarray, rather than just for the entire system. This allows us to model a broader set of system configurations than was previously possible. But we do still provide some reference information about your total system size up at the top here. So you'll see that in subarray 1, in this default case, there are 7 modules per string and 2 strings, resulting in a total of 14 modules in subarray 1. And since there's only one subarray, that also is 14 modules for the entire system and 2 strings for the system. And you'll see that our total DC capacity is also displayed up at the top so that you can still keep track of what these inputs are doing to your system size. Number of inverters is still here at the top of the page. And the DC to AC ratio is displayed as a calculated variable underneath that so that you can have a little bit of information on the ratio of your system sizes as you take a look at your design. I'll also point out that we have down here some information on electrical sizing. This deals mostly with string sizes, and I'll demo that in a little bit. But between all of these different calculated variables, we're providing information to help you size your system in a way that makes sense. So the other page that changed for the multiple MPPT inverters is the inverter page. So if I click on that, you'll see it looks fairly similar, but we have a new input, the number of maximum power point tracking inputs for that inverter. All of the different inverter models within SAM have an input associated with that. So for example, if I switch over to the inverter datasheet model, you'll see there's an input for a number of MPPT inputs here as well. But I will switch back to the database option for now. So now let me go ahead and actually start demonstrating some of the modeling flows in SAM. To start with, I'm going to pick a larger inverter just to make it a little bit interesting from a system sizing perspective. I went through in advance and picked out a pretty sizable inverter, 823 kilowatts here, that I'm going to go ahead and use for my demonstrations going forward. So if I go back to the system design page, you'll see that now that I've picked a much larger inverter, things like my DC to AC ratio being 0.01 and the subarray 1 string sizing messages showing up give me a clue that I'm going to want to make some updates on this page. You can also see up at the top that my inverter AC capacity is now 823 kilowatts because I picked an 823 kilowatt inverter on the inverter page and said that I have one of them. So I'm going to want to increase the number of modules to go with that inverter. So as a blind start, let's start by switching from 7 modules per string to 9. You can see that it updated the number of modules in the 2 different places here, but it's still telling me that the subarray 1 string voltage is below the inverter minimum and that I should consider using more modules per string. So to demonstrate what happens in the other direction, let's say I say, okay, I'll use 13 modules per string. Now you can see that my sizing message changed and it's telling me that the string voltage is exceeding the inverter maximum rated voltage at reference conditions and I should consider using fewer. So since I went through this system in advance of this webinar, I know that 10 modules per string is going to work well with the module and inverter choices that I've made and result in no system sizing messages down here. So now that I've picked the number of modules per string to work with this inverter, I need to pick the number of strings in parallel to get a DC to AC ratio that I am looking for. So in this case, I'm going to pick 300 strings in parallel, bringing me to a DC to AC ratio of about 1.2 and a nameplate DC capacity of about 1 megawatt. And this is going to work for the demonstration system that I'm looking for to show you some of these multiple MPPT options. So just to check that I've done all of this correctly, I'm going to go ahead and simulate the system here. You can see I get a pretty reasonable capacity factor, and I'm happy with this option. So I'm going to go ahead and rename this case as my base design. Then from here, I'm going to start making some changes to demonstrate some of the inverter modeling options going along with maximum power point tracking. So if I click on the case, yeah.
Could you take a minute to show us which module you're using?
Sure. If I go up here to the module page, in this case, I was using the default module that was selected in SAM when I started up. So for this one, it's a SunPower 335 watt module. And so if I flip back to the system design page, you can see that the characteristics that were displayed on the module page as far as the voltage information is what is used to calculate these string voltages shown here under subarray 1. And these string voltages are then what are compared to the maximum power point tracking voltage range that is an inverter specification. And that's what results in these sizing messages, is the comparison of these string voltage conditions calculated using module information to these inverter voltage characteristics from the inverter page. Does that answer the question?
Yes, thank you.
Great, thanks. So now that I've gotten some results for this system, I'm going to go ahead and duplicate this case to create a system that's a little bit more complex. I'll rename it, and in this one I want to model a system that has different strings. So I'll go ahead and rename it to the different string system and go back to my system design page. Now what I want to do here, because I want to change the string information, is I'm going to enable a second subarray, which will cause all of the inputs for subarray 2 to show up. Now I'm going to assume in my fictitious system here that all of my tilt and azimuth and tracking information is the same, but for whatever reason, this section of the system has more modules per string. So I have a section of 12 modules per string instead of 10. And let's say that I want the same overall system size, which would be 3,000 modules. I'm going to put 80 strings of my 12 modules per string, and then I'll back down subarray 1 so that it's at 204 strings of my 10 modules per string, which gives me that same 3,000 total modules as my base design here. So if I go back to my different strings case, I will go ahead and simulate this one. And we can take a look at some of the results. Now I want to remind you that in this case, the system design features strings that will have different operating voltages. But I did not set up a multiple MPPT inverter or the mismatch calculation yet. So what Sam is doing here is using the weighted average voltage of all of these strings as an input to the inverter. That's not quite right from a modeling perspective. It's a simplifying assumption. But let me go ahead and see what it looks like if I get rid of that simplifying assumption. So again, I'm going to duplicate this case with my 2 subarrays. But now I'm going to look at the case where I have these different strings, but I'm calculating the mismatch due to the voltages being different between those different strings. So on the system design page here, if I scroll all the way down to the bottom, we'll see an expandable tab called PV subarray voltage mismatch. If I click on that to expand it and then scroll a little bit more, I see an explanation of what that feature is going to do. Basically, it's going to allow the inverter to seek a global power maximum given these different subarrays throughout a range of voltages. And then when it finds the global power maximum, it will use that voltage to operate both subarrays, because we're assuming here that it's still going into one maximum power point tracking input, and it will give me results based on those voltages that it calculates. So if I click this checkbox, that turns on the subarray mismatch calculation, and then I can go ahead and click simulate. Now this takes a little bit longer because at each time step, SAM is causing the inverter to sweep a range of voltages, but you can see that for this particular case, it doesn't add that much simulation time. However, it does change the answer. So in this case, where I have the mismatch calculation turned on, I have a capacity factor of 18.9%. But when I was using just the average voltage across the strings, my capacity factor is 19.3%. So I did the math out before this webinar, and if we look at the annual energy numbers, that's a difference of just over 2% annually, that the system operation will be lowered when you take into account the mismatch between the voltages and the different strings. So if possible, when you're looking at systems that have some mismatch on the voltages between strings or subarrays, we recommend using that voltage mismatch calculation because it will more accurately represent what the real-world inverter is going to do. Now, as I mentioned, it's not possible for every module model. So if I go back to the module page, you see right now we have selected the CEC performance model, which is our default option and probably the most popular. But if I click on this, we do have some other module model options here. And I want to highlight the simple efficiency module model and the Sandia PD array performance model are the two models that cannot be run with the voltage mismatch calculation because they don't provide enough information about the entire IV curve to allow us to simulate off maximum power point operation. So that's why I say when possible, we recommend using this option. But it isn't always possible, and SAM will warn you if you try to run it in a situation where you can't. So let me flip back to the results here. And we'll notice that with this system, when we calculate the mismatch, my capacity factor is 18.9%. So now let's get into the realm of multiple maximum power point tracking inverters. If I go ahead and duplicate this case, I'm going to see what happens with the same DC system, but assuming that I have an inverter that has multiple MPPT inputs. Now, one note about this when I go to the inverter page is that the number of MPPT inputs on an inverter is usually an inverter specification. However, unfortunately, in the inverter library database that we have, there is not enough information for us to pull out automatically how many MPPT inputs an inverter has. And that's why this is currently a user-specified input instead of a calculated input based on the database. Some of the inverter names do tell you when it has multiple MPPTs, but it's unfortunately not consistent enough for us to be able to parse it out automatically. So in this case, let's say that I have two different subarrays, so I want to model an inverter that has two different maximum power point tracking inputs. I'll go ahead and change this input to 2, and then I'll go back to my system design page. And you'll see here that compared with the system design pages in the other cases, there's a new input for each of the subarrays called the inverter MPPT input for that subarray. What this is asking you to do is to map each subarray to an MPPT input on the inverter. And we've also provided an option to have SAM help you do that automatically with this button that shows up when I specify an inverter with more than one maximum power point tracking input. So this set subarrays for multiple MPPT button, if I click it, we'll go ahead and change the MPPT input for each subarray so that we have one subarray on input 1 and one subarray on input 2. Now, if I had typed that there were 3 MPPT inputs and then hit this button, it would have also enabled subarray 3 for me and assigned it to maximum power point tracking input 3. But let's assume here that because I only have 2 subarrays, I'm going to use 2 maximum power point tracking inputs on my inverter. And I'm going to turn off the mismatch calculation here between the subarrays and simulate my system again. So let's compare the multiple maximum power point tracking inverter to the case where we have a single maximum power point tracking and the mismatch is accurately modeled. So you can see that when we have the intra-subarray mismatch, my capacity factor is 18.9%. But if I look at the case where I can hook those subarrays up to different maximum power point tracking inputs, it boosts my capacity factor to 19.3%. So that's an improvement in performance by about 2%, which is sort of coincidentally the same amount of performance loss that we saw by not modeling the mismatch accurately. That will not always be the case, so that's why I say it's sort of a coincidence in this case. So that is my quick demonstration of how to use these different ways of modeling subarray voltage and maximum power point tracking in SAM. I want to switch back over to the PowerPoint real quick to talk a little bit about some of the limitations and future work of this model. So currently the maximum power point tracking is enabled for a one inverter system. So I couldn't have, for example, 3 inverters that each have 2 maximum power point tracking inputs at this point in time. And that's mostly a user interface limitation. It will require some fairly significant user interface redesign in order to make that possible. So we wanted to take smaller steps towards that level of flexibility with this release and start with not quite as massive of a user interface change. But we do hope to be able to enable that in a future version of SAM. We would also like to enable more than 4 maximum power point tracking inputs on an inverter. Again, this is a current user interface limitation. Because we only have 4 subarrays in the user interface, it only makes sense to have 4 maximum power point tracking inputs because the user interface doesn't allow you to specify more subarrays than that. Again, in the future, though, that's something that we hope to be able to rectify in the user interface, and it is something that we could make possible in the code for all of you software development kit users, where you would be able to model more maximum power point tracking inputs because there is no user interface limitation. Another limitation of the current model is that you cannot model a DC connected battery with a multiple MPPT inverter. You can model an AC connected battery, but again, the DC connected battery would need to be connected to a specific input on the multiple MPPT inverter, and so we took a sort of first step in that direction with this model, and we hope to expand the types of configurations with DC connected batteries in future versions dealing with multiple MPPT input inverters. A little bit outside the field of what I was showing, but still a feature that often comes up when I talk about multiple MPPT inverters is the representation of DC power electronics. So DC to DC optimizers and that type of thing. The multiple MPPT inverter feature does not actually help model DC power electronics correctly, although there are 1 or 2 ways that you could sort of hack the multiple MPPT feature to better represent a system with DC power electronics. But it is on our list to improve the representation of DC power electronics specifically. to be able to be used with all types of inverters, both single and multiple MPPT inverters. And the last possible future work item is to maybe be able to combine multiple types of modules in a string. So earlier in the presentation, I mentioned that that could be one time when you might have different voltages between different strings, is if you have modules by different manufacturers or even by the same manufacturer but different models. That currently still can't be modeled in SAM, but we would like to investigate being able to model that in a future version. So with that discussion of some of the limitations of the model, I'll go ahead and move a little bit early to the question and answer part of the webinar today. And thank you all for your attention so far, and we look forward to having some discussion.
Thanks, Janine. We do have a few questions.
Sure.
So the first one is, I guess the most recently asked one is about the new feature. So this new feature will not allow two different sized inverters in one project. Is that a plan for the future?
That's correct. That is another thing that I probably should have listed on the future work slide, is that yes, this currently only allows systems with one type of inverter. We would like to look into some options to allow systems that have different types of inverters. We have not yet decided whether that will be contained within one case or whether you would set them up as sort of almost like they were separate projects, but have a way to combine them when you're looking at a financial modeling perspective. So that's still sort of to be determined, but yes, it is on our list to allow that type of flexibility as well.
Okay, and then the next question is, when we change the MPPT number from 1 to 2, does SAM treat each MPPT as half of the original inverter? Does SAM do it similar to PV Syst, that the MPPT voltage current parameters are halved?
Right, great question. So SAM actually treats it a little bit differently. We model the inverter as a whole rather than as almost like two separate inverters, which is why we don't require the user to specify basically a split of the power between the two different MPPT inputs. And then when we model the power coming out of each subarray, after we've modeled those, we add them together to check it against the overall inverter limitation. So for example, if you had a 10 kilowatt inverter and you model two subarrays that produce approximately 5 kilowatts at their peak, we would model each of those MPPT inputs separately and then check the total against the total inverter capacity. So if each of those subarrays had a really good day and produced 5.1 kilowatts of power for a total of 10.2 kilowatts of power, we would use that total number to check against the inverter specification being a 10 kilowatt inverter and to clip appropriately. So it is a little bit different than the PV Syst model currently.
Thank you. And then there's one more that I see here is there a way to use this improvement in multiple MPPT modeling to better model an inverter with string and DC optimizers?
So, sort of. It's a little bit hacky and probably something that I would want to think through not live on a webinar. But what we would probably need to do is something a little bit more complex where you were to set up as if it were one module per string and having multiple MPPT inputs on an inverter that in reality did not have multiple MPPT inputs. Now, this is greatly limited by the current user interface limitation of only 4 different subarrays. But there would be some options depending on the system configuration to be able to sort of, in a hacky way, represent DC optimizers using this multiple MPPT feature. If you are interested in presenting us with a system configuration and working through how to hack SAM to model it with us, I would encourage you to either post on the support forum of the SAM website or to send an email to our sam.support@nrel.gov email, and we can work with you and then maybe post that as an example of one way to hack this new feature to better represent DC optimizers.
Great, thanks. If you guys have questions, feel free to continue to type them. We're still monitoring the questions, or if you wanted to follow up on one that you already asked, you can type a follow-up question. There are a couple more here. One is, can we connect an inverter that uses MPPT and an inverter that uses another technique in the same system?
Currently, no, because the multiple MPPT feature is enabled for only one inverter systems. But that would be an option that would sort of inherently come with some of the future work that we're discussing, where you might be able to model different inverters in the same system. So you could basically model one inverter that had multiple MPPT inputs and one inverter that didn't, that just had strings connected, even if there was going to be some string mismatch, and look at the effect on the total system of those options.
All right, and one last one here. This is sort of a general question, I think, but if there's more than one inverter in a real system, are there a master inverter and slave inverters?
My understanding is that you can hook up some inverters to behave in that way, where the master inverter does the majority of the maximum power point tracking, and the slave inverters, my understanding is, follow that master's lead as far as what voltage levels they're going to be using. We did not implement that necessarily in SAM because from a modeling perspective, that's fairly similar to what SAM currently does when you have multiple subarrays connected to the same input on the same inverter.
Great. And then here's a question basically just saying that this feature is not in the current version. So just make clear that the version that Janine demonstrated is an internal development version that we'll be releasing this fall, hopefully at the end of the month. So the capabilities that we saw in this webinar are not available in the current version of SAM.
That's correct. We do have it in a beta version currently, so if anyone's really chomping at the bit to try it out, we can send that out. And for the SDK users, at least one of whom I know is on the line right now, I do have a couple of people on my list to send the SDK beta out to test out this feature for us. So there are some options if you are a power user or someone with a whole lot of multiple MPPT systems. We would love to hear from you to help us test this new feature.
And then what is the climate condition that you use?
Great question. Let me switch back over to SAM. In the systems I showed, I used the default solar resource file, which in SAM is Phoenix, Arizona. In our upcoming version of SAM, we're, as I mentioned, switching the way that the location and resource page operates a little bit. But the default uses the latest NREL National Solar Radiation Database information. There's a model called the Physical Solar Model, or PSM version 3, which is the origin of the PSM v3 in here. And some of those files are shipped with SAM in order to be default files for our different cases here. And so most of the PV cases, the default files in Phoenix. And I just used that in my demonstration. That said, you could easily use any other location to do the same type of analysis. It does not require any extra climatological information than a normal PV simulation does. So anything that is usually covered with by a SAM solar resource file would continue to be covered when using a multiple MPPT inverter. So in the PSMV3 case, that covers most of North America and about half of South America and some of India and the surrounding countries. And then there's other databases to get weather files for other parts of the world that we talk through more on our weather page on the SAM website, sam.nrel.gov/weather, which I could show real quick here.
You could also mention the webinar on the new solar resource page.
Yes, excellent. So we have a lot of resources available on the SAM website. The first one, you'll find recordings of all of our past webinars, and this webinar will also be posted there after we finish processing it. But you can find the webinar about solar resource data posted here under recordings of past webinars, and that walks through the new solar resource page in SAM and how to download data from the NREL National Solar Radiation Database that we've mentioned. Looks like there's another part here too from the NSRDB that talks more about that model. And it also discusses where you can find resource data for other areas of the world as well that aren't covered by the NSRDB.
And
anything I'm missing there?
Benjamin's particularly interested in Mexico, so the NSRDB does cover Mexico. So with the new solar resource page, you'll be able to type in a street address in Mexico and get a weather file for your site.
Right. We have an image of the map that the NSRDB covers on our weather page on the SAM website, and information about how to access data from another source that works with SAM that covers much of the rest of the globe as well.
And then we have another question. This is unrelated, but can you tell me if it is possible to model power factor and limit of maximum inverter output power?
That is a great question. It's not currently a feature in SAM, but we have some work that will be happening this year to take a look at PV systems that are going to be operating off of unity power factor to provide ancillary services or something like that. And that will likely include some type of export limit or a limit on how much power can be delivered by the system, as well as a couple of other sort of options for how to configure the way that your system interacts with the grid. So we're pretty excited about that work. It's going to be sort of a new thing for SAM as a whole. It will be looking a little bit more at how the system interacts with the grid from more than just a price perspective. So if, again, we always like to have people who are willing to beta test or give us input on some of those new features that we're designing. So if that's something that you know quite a bit about and would like to share some of your knowledge with us on what types of things could be helpful in that model, definitely please feel free to reach out to us and let us know.
Here's a question about cable sizing. Just says,
PV, like electrical cable sizing?
What modeling cable sizing? Yeah, I think maybe it's a question about wiring losses.
Right. So in SAM, we do not explicitly model wiring losses. There are some tools that do that. Instead, we have some sort of simplistic loss assumptions. If you go to the losses tab within SAM, you'll see we have an input for DC side wiring losses, and then also an input for AC side wiring losses that are applied at different places within the model. And so we, like I said, use more of a simplified approach, just representing the wiring losses as being constant throughout the year as a percentage of produced power, rather than something a little bit more sophisticated looking at actual wiring sizes and lengths. As I mentioned, there are some other tools that go into that in more detail, so if that's something that's a big part of your system design, you might want to consider some of the tools that look in a little bit more detail at the bottoms-up electrical configuration of the system.
Okay. Don't see any other questions. We have a few minutes left if there are any other questions.
Well, perhaps in the meantime, I will also show on the SAM website the download page, which I'm sure most of you are familiar with, but this is where we'll be updating when the new version of SAM comes out. That includes this multiple maximum power point tracking feature, includes the new solar resource page that we've been mentioning, and also includes the other hot topic in our three webinar series this fall, which is the ability to model bifacial modules that we have added to SAM. So all of those will be coming out in the upcoming version, which we'll post on the download page. And if you're currently an active user of SAM, we also typically send out an email and it will show up in your version of SAM when there's a new version available to help people keep up to date with what's available. And note that all of the webinars that I mentioned, including the bifacial one, are posted on that webinars page on the SAM website.
All right, I don't see any other questions.
All right, well, if there are no other questions, maybe we'll give everyone 8 minutes back out of their day. Thanks everyone for your attention in the webinar and for the great questions. And we're looking forward to hearing your thoughts about the new MPPT feature when it comes out. And as always, feel free to reach out to us via the support forum or the support email address with questions or comments. Thank you. Have a great day, everyone.